Analog low-pass Chebyshev type 1 transfer function. This filter results in an all-pole transfer function, just a meaning of all-pole, that is, its zeros are as many as its poles and are located at infinity. For the low-pass Chebyshev filter of the first type, we have abs of h of omega prime is equal to abs of h of omega over omega p to the power of 2. So, leading to 1 over 1 plus epsilon to the power of 2 times Cn to the power of 2 of omega prime. Okay? You see here the substitution. Omega over omega p is equal to omega prime. Anyhow, where epsilon to the power of 2 is 10 to the power of 0.1 times Rp minus 1. Rp, of course, definitely greater than 0, passband repel in dB, or equivalently 1 over 1 plus epsilon to the power of 2, which will be equal to 1 minus delta p to the power of 2, and is equal to 10 to the power of minus 0.1 times Rp. And Cn of omega over omega p is a Chebyshev polynomial that generates equirepel in the passband. Okay? Here, just notice to the role of cosine inside passband. So you will have oscillation, but cosine hyperbolic, no ringing, no oscillation in a stop band. Right? Now, just leave the rest of the equations because they are really difficult to understand. Butterworth was the simplest one. Okay? So the rest, Chebyshev type 1, type 2, or especially elliptic, we don't want you as an engineer to learn them because they are useless. It's enough to use just applications related to the what we mentioned. Anyhow, just having a very fast look and saving the time of recording, which we have, of course, limitations everywhere. Here you see table 7.1 demonstrates the Chebyshev polynomials from n-1 up to 9. N is the polynomial as well as the filter degree. Just leave everything. Okay. Later, if you are interested, you may study them. How to estimate the degree of the filter. Very simple equation. Here you see the frequency response for n being equal to 1, 2 starting repels, 3, 4, 5, 6 repels in passband without any repel in a stop band. Okay? We just mentioned it. Now, how to use them as an engineer? That's the key point. Design an analog low-pass Chebyshev of type 1 for the following specification. Passband edge frequency, again, similarly, 2 kHz. Delta F, 800 Hz. Attenuation in the stop band, 40 dB. You see here, similar specification. Passband repel, less than or equal to 0.1 dB in passband. Now we are going to run the program. Okay. Here you see frequency response, of course, amplitude apps. repel in passband, and stop band without any repel, and green line showing what we have computed for passband and cutoff, and the red one cyan line, just please be careful about the cyan and green and red line. Okay, what's the meaning? We'll just point it out. So declaration analog Chebyshev 1, import, just leave them. Estimate degree, similar to what we mentioned for Butterworth in the previous recording. Cutoff, calculating cutoff for Lowpass, and a stop band. Here declaration, the stop band is equal to fp plus delta f for, of course, Lowpass, not always, delta p, delta s, omega p, omega s, estimate degree. Okay, now the main syntax, num and denom will be equal to signal dot Chebyshev1 n ap omega p, b type low, analog type true. So if you change b type to high, and of course with the correct values for ap or omega p, it will be high pass, and the same scenario for band pass filter and band stop filter. You just need to have some practice, and the rest are the same. Here we get omega and h from the syntax fric s, num and denom and omega, and showing the results very simply. Now, use Cheb1 function to estimate the degree of the filter and compare the results with what you got. Find and plot the location of zeros and poles. Find and plot the phase response too. Do a research with modified parameters every time we ask it in any take-home. Compare and write a technical report related to the quality of the results and degrees of the filters for Lowpass, Butterworth, and Chebyshev of type 1 filters. Just compare them and discuss your opinion. Which one do you prefer? And the next question, try high pass, band pass, and band stop filters too. Right. Analog low pass Chebyshev of type 2. Another name of this method is inverse Chebyshev approximation function. Both finite poles and zeros exist in the transfer function. The passband is flat, but the stop band has ripples due to the presence of zeros. This method leads to a better phase response than the Chebyshev method of the first type, but on the other hand, its computational complexity for the design is higher. Okay, I leave the exact definition for you yourself to read out them. Here you see the frequency response, of course, for amplitude, degree 1, 2, 3, 4, 5, 6. Here you see repels in stop band, but no repel in passband. That's Chebyshev of type 2. Okay. Now, next figure shows frequency response of Chebyshev low pass of type 2. We just mentioned it. Now, example. Design an analog low pass Chebyshev of type 2 for the following specification. You see, we have tried to keep the specification as much close to each other to provide a comparison environment for you. Again, passband frequency 2 kHz, delta F 800, stop band attenuation 40 dB, and a ripple in a passband 0.1. Now we are going to run the program. Okay, let's run the program. Here you see low pass filter of Chebyshev of type 2, ripples and stop band. Again, 3 lines showing the results for passband, cutoff, and stop band. Now, analog Chebby 2, import, just leave them. Similar idea, and stop band, and declaration for T 0.1, 800, 2000 for passband. Okay. This time you use Chebby 2, and instead of omega p, you just need to insert omega s. B type is still low pass, and analog type is true. So just notice to the major syntax, and the rest is similar. Okay. We don't have any more time to record. Now, similar take home. Use Cheb2 OR function to estimate the degree of the filter and compare the results. Find and plot the location of zeros and poles. The phase response. Modified parameters are needed. And compare and write a technical report related to the quality of the results and degrees of the filters for low pass butter, Chebby 1 and Chebby 2. Now, another new environment has been added to the comparison. So you just little by little learn how to write a technical report and compare their methods. And again, similarly, try high pass, band pass, and band stop filters for Chebby 2. Now, elliptic, low pass elliptic. The other name of this filter is cover filter, and to provide assume similar characteristics, it leads to the lowest filter degree. Okay? Possible with the assumption that both pass and stop bands will have ripples. Also, its design complexity more than Butterworth and Chebby, meaning that human being is not able to analyze them. You need computers, tables, and other facilities. For elliptic low pass, the transfer function is as follows. Apps to the power of 2 is equal to 1 over 1 plus epsilon to the power of 2 times Rn to the power of 2 of omega over omega p. I just skimming will have a skimming. Now, you see the frequency response, degree 1, 2, 3, 4, 5, 6. So in 6, you see here ripple in passband and stop band as well. Okay. Now, design an analog low pass elliptic for the following specification. Similarly, 2 kHz for FP, delta F 800, AS 40 dB, AP 0.1. Now we are going to run the program inside PyCharm. Okay, let's run the program. Ripple in passband and stop band. Okay, here you see the degree of the filter, 6 suffices. And what about the lines? Blue for here, the main frequency response, cyan for passband, green for computed cutoff, and red for computed stop band frequency. Anyhow, going back to the lecture note, similar topic, similar syntax here. Now, take home. Find and plot the location of the zeros and poles. Find and plot phase response. Do a research with modified parameters. Compare and write a technical report related to the quality of the results and degrees of the filters for low-pass butter, Chebyshev 1, Chebyshev 2, and elliptic newly added. And try high-pass, band pass, and band stop filters too.